This conference will now be recorded.
Okay, tonight we are going to talk about history, computing history, the most important computing history you are likely to hear about. Not just the history, but what it led to. What I'm going to be covering is a paradigm shift in computing called client-server computing. This all happened in my lifetime. So I've seen it. I've worked in it. I even went to the college where it all started. So just last week was an important anniversary. October 29th, 1969 was the day the very first bytes were sent over a computer network. The network was called ARPANET. That was Advanced Research Project military network. Okay. It was done at UCLA, which is where I got my Mathematics of Computation degree. It's done in the building that I took my classes in. Somebody at UCLA tried to log into a computer at Stanford University, and it crashed. They were typing the word login, and they got L and O sent before it crashed. So that was the first message, L and O. So what was computing before client-server computing? Well, that's simple enough. You just had computers. They didn't talk to any other computers because there were no networks. Maybe they had the ability to send data to a printer, but they weren't really sending it over a computer network. Like today, we can plug in a USB printer, but that doesn't mean the printer is on the network, right? Get the difference there. So big computers, mainframes, right? The early mainframes started in the 1940s, 40s and 50s. Then the transistors came along in the late 50s, and they started building smaller computers. They were still, the mini computers is what some people call them, but still no computer networks. But the research did start, right? And by 1969, a communication network had been set up between UCLA and Stanford. It's funded by the government. Those first messages were sent, and then things just exploded. And they exploded, I mean, for lots of reasons, right? Advances in technology. If you look back at the 70s, you'll see that that's when the microprocessors first came out. So the Intel 4-bit processor, 8-bit processor, 16-bit processors, all the the computers of the 70s, the Apple, the Commodore, the TRS-80, those computers, I guess it was the Commodore PET probably. Those were 8-bit computers. They were using I think all of them were like a 6502 microprocessor, maybe a 6510 in one of the later Commodores. The Ataris came along and they were 6502 based 8-bit computers. Now we're on 64-bit. Just 40 some odd years later, 45 years later, we've gone eightfold in our data pathways and how much data we can send in parallel in and out of a computer, which controls how much information it can send in and out, right? And so how fast it can process information, because it gets information so much faster. It gets it in big chunks because of wide data buses. Now, the other factor, and this is kind of I guess I'd say a philosophical factor. There is a law called Metcalfe's law. And what it says is that the value of a network, and this could be any kind of network, frankly, but we're talking computer networks. It could be a people network is what I mean. Is another example. But the value of a network grows proportional to the square of the number of nodes in the network. So if I just have one node, I don't get any value, any growth. It's just one. And what's the square of one is one. Now, what if I have two networks? Oh, well, I've doubled my power. If I have three networks, well, I've got more power. I've got more connections. I don't know if it's really the square of the number of nodes. Yeah, that might not be accurate. But regardless of that, the more nodes I add in the network, the more communication pathways I create. And that number grows exponentially. So by the time I have, you know, four nodes, well, each node, each computer in the network can talk to three other computers, right? So that's a dozen network pathways. Now I keep adding those and it keeps growing exponentially, right? This created value. That's basically what Metcalfe was saying. The bigger the network, the more valuable it becomes. Now we have a network with billions of nodes. That's just, between computers and phones. Actually, between computers and phones, there's probably, there's more of them than there are people, right? And then when you start throwing in today's IoT devices and they're on networks, you quickly start to see, I hope that you realize that there could be hundreds of billions of nodes on networks today. They can't all communicate with each other. Some are still autonomous systems. Now, as this ARPANET grew, some communication protocols for the new paradigm, the client-server computing paradigm, started to establish and grow. Because sure, you could send data back and forth between a couple computers, but how did you do it? People realized you needed to have standardized commands to send data back and forth so that other people could then take that standard and build their own version of it on their computer. So now multiple different types of computers could talk to each other over a network and use a standard protocol for communication. What was that protocol called? It was called Telnet, Telnet. So Telnet enabled computers to send commands back and forth to each other. The commands are typically, like 3-letter abbreviations of commands. There's another client-server program that came along at the time, FTP. It's also really old, 1971. Telnet's from 1973. So FTP is the file transfer protocol. So people immediately realize, hey, if I'm going to, do something useful with computers, I'm not just going to type information in. If I already have it typed in, if it's already in a file somewhere stored, maybe I could send it. Now, storage in this era, this is before there were hard drives, before there were floppy drives. Some of the research, again, was probably going on. People were trying to figure it out. Things were being stored on magnetic tape, okay? So if you're going to send a file to somebody, you load in the tape, find the file on the tape, load it into your system, and kind of maybe it gets in your memory. Probably not. Memory was probably too small because it's too precious, too expensive. And the file could actually, maybe it's a pretty big file. So I'm guessing that a lot of the files were maybe read as they're being sent, so that you're not taking up too much memory. So you would use input-output buffers, small containers of memory. Read a little data from the tape drive, comes into your input buffer, and then you write it into an output buffer connected to the network. And so your file transfer protocol, your FTP client, was going to be using those buffers to manage the communication so that you don't overwhelm and overload the memory on your computer. And it would send it to a server. So client server computing. You have a remote computer, which is the server, and your local one is your client. So you would have a client protocol that could talk to a server. FTP, you'd have an FTP client to talk to an FTP server, a telnet client to talk to some other telnet system. So I can show you some of that right now and what people did with it, because it got pretty interesting pretty quick. People started realizing, hey, I could run my own computer and put it on, a network, or have a way of allowing people to connect to it. And this started happening, I guess I'm going to say early 80s. Maybe as early as the late 70s. But in the 80s, people started to have these things called modems. And like I said, they might have probably had some in the 70s, but in the 80s, it went a little more mainstream. And as more and more people got them, because of Metcalfe's law, it created more value, a bigger network. And so people started figuring, oh, well, I can do something. I can connect these people together. So we entered the age of the bulletin board system. So like a bulletin board, a real one, a physical one, you post information on it. So a bulletin board system was a computing system that you could post information on. I connected on some, I guess it was must have been the early 90s. Again, pre-internet, or pre-World Wide Web, I should say. The internet did exist at that point, but it wasn't very big. But you could get these modems and hook them up to your computer, and they would hook up to your phone line. And they were acoustic modems. So they would send tones, beep, 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 tones over your phone line. That would encode the data, the bytes that were being sent. So I remember being on one that was auctions. They were selling stuff, and so you could see what was for sale on this bulletin board system. So you could log in and get an account, or maybe you were just a guest on the system. Now, people enjoyed these things. They enjoyed them so much that they're still around today. And some are accessible over the internet. So that's what I'm going to show you. I'm going to show you some telnet capabilities. So we're going to share our window now. So I have a special system installed on my Windows system that I use for software development. It lets me write cross-platform C++ applications, because I do some development work still. So right now you're seeing my window, Min GW64. It's like minimal gateway, something like that. It's a minimal system for compiling software, cross-platform compilers, cross-platform tools like the GCC. Like if I show you some commands here. So this is like a, which GCC. Okay, so this tells me where my GCC, my new compiler program is. And then I could probably like check its, I don't know, this might tell me the version. Maybe I got to do two dashes. There we go, 2 dashes. So there's some more terminal commands for you. Rev 8, built by the MSys2 project. So MSys is the creator of this Min GW system that I'm in. So this has all kinds of commands built into it. I don't even know how complete or know what this is. It's going to look a lot like Linux, but all that means is it looks a lot like Unix, which means it looks a lot like POSIX. All these historical systems that our modern systems are based on. So I do have a telnet command though, and I went and looked up the addresses of some bulletin board systems so we can visit one. We're going to visit one called The Cave. And that's not the right site. Bizarre. Well, we'll go check it out. Their history link is broken, but that's okay. These things, some of them have been around since the beginning, since the 80s. And so you can go and look up. I'll put this in the chat. I'll put up this web link if you are curious, because you don't need any special tools to do this. But what you would be experiencing is client-server communications, since that's what we're talking about. So back to my window here, I'm going to telnet to that address. Let's see what this does. See if I'm executing the command right. Trying to connect, connected. Oh, well, we're at the cave. And notice the curious graphics. There weren't very many colors available. Some of the sites, this is actually pretty sophisticated. They actually have graphics. Some others out there, they just have text, pure text, and they use text to make little symbols and characters and things. So let's see. Node 1, Windows NT version 6.1. That's what the server is running. It knows the day. There's the admin. Knows where I'm coming from. So I'm coming from, that's my IP address, or the domain, basically. That's my IP address right there. You all know how to get IP addresses now, don't you? So I'm going to type new because I'm new. Hey, well, new. New user registration. Hit your backspace or delete left. Okay. Mouse reporting. I'm going to say yes. Yeah, probably does that too. I'm going to make up an alias here. There. That's good. Enter your location. We'll say Virginia. I guess I got to go through all this stuff. Network email address. There we go. Yes. Okay, native multi-threaded bulletin board system software for the internet age. And look, it has FTP. It has several client-server programs here. So we have Telnet, which we're using right now. R login, a remote login. SSH, that is a secure version of Telnet. All of the data sent by Telnet is sent as clear text. You could just read this. I could be looking at Wireshark right now and seeing all the Telnet information in Wireshark. Maybe I'll do that. Do I have Wireshark installed? Let's see. I don't have it installed, but I'm pretty quick about these things these days, the modern internet. So FTP, SMTP, Simple Mail Transport Protocol, POP3, Post Office Protocol, which is mail, right? Post office. Web. So it's got an HTTP, Hypertext Transfer Protocol. That's what created the World Wide Web, and we'll talk about that in a second. Okay, Yeah, that's fine. Okay, Wireshark's installing. Finger, Gopher, and IRC. Gopher was a primitive search engine. You would execute a command from your Gopher client, and it would you wouldn't have to sit there and wait for it because it might take an hour. IRC, Internet Relay Chat. So as an early, messenger, that kind of thing. Okay, so I've got Wireshark. I'm curious what I'm going to see now if I run it. Let's see if I can filter on Telnet and get some of the plain text data. We so seldom see plain text. Okay, so there's a lot of something going on in my Wireshark. Okay. There's some basic information, private messages, show the time, list users online, that kind of thing. Wow. Okay, so system users, 19 logons today. Okay, interesting. Okay, I've captured enough data, I think. Let's see. So all this data that it's showing me, I'm going to guess was plain text. So we're going to try to filter this out. So we're going to use some other networking commands. So I need to look up the IP address. Okay, so I used NS lookup, and I just got the IP address of the cave. I know I use that command because I know a bunch of you. Let's just show you. We're doing this just recently. Show the PowerShell window. So there's the IP address from the cave. So I'm going to use this as a filter in Wireshark. I think this ought to work. Just got to change the destination IP. And I got it. This is going to be interesting. I'm not seeing readable data at the moment, though. Maybe we will. Give me a second here. Well, this will be instructive anyway. So we're going to take a look at my Telnet session data using Wireshark. All these networking tools. See how it all comes together. Where did my Wireshark go? There it is. Okay. So I filtered out so that all the traffic had a destination of that IP address I just showed you for the cave bulletin board system. So it's coming from my system. And you see the protocol, Telnet. That's kind of cool. We know that it's doing its thing. Not a whole lot of data. So what I'm probably going to do is I'm going to filter on the protocol Telnet instead. And then we see the traffic that went back and forth, right? So I sent something, and then they sent something back to me. And remember what I was telling you about it being not encrypted? Well, this is great. Here's the perfect example. Remembering these keys will help you enjoy your Synchronet experience. So right here, this is the raw telnet data that I'm showing you here. And it's the same stuff that you had seen on the screen. So we're going through it. And then I hit a key, or it told me to hit a key. I hit a key. It sent one byte because hitting a single key is 1 byte. And then it sent a bunch of data back. This is the Cave BBS located in, oh, it's Raleigh, North Carolina. Well, there you go. Kind of neat. So, um, yeah, so that we're done with that demonstration. So, client server, telnet communication protocol. So we're just gonna quit. Okay, so that's all shut down. So bulletin board systems were built on telnet, and they sprang up all over the place. Right, people had computers, and they lasted. Well, there's, like I said, they're still around today. Obviously, they're not used as much as the internet, but people were playing games on them. They were, exchanging information. And there's all kinds of articles. And that website link I gave you has articles to, the lost civilization of dial-up bulletin board systems. All the big magazines, people writing about computers that people used, the vintage computer systems today. So people are still using the old computers to run the old systems, which is kind of cool. So what else on client server? So what happened next, right? What's going on next? Well, next came really was hypertext transport protocol. Sir Tim Berners-Lee wanted to share documents, scientific documents and papers in an easier fashion than using FTP and Gopher and Telnet and all these arcane command line interfaces. He wanted a visual interface, and he had certain ideas in mind, some certain verbs, okay, that he wanted to build his system on and make everything pretty simple. And so he had verbs like get and verbs like put, and there's a couple others, but put and get are the pretty good ones. So if you look at HTTP's protocol today, you'll see that, gosh, let me show you how to look at the protocol. We're going to switch windows again. Now that we've got Wireshark, we'll what window will we look at? I'm going into my browser, and what I'm going to do is I'm going to into the menus to get to more tools. And what I want to launch is I'm launching developer tools, okay, for our website. So now I'm going to change the window I'm sharing so you can see what the developer tools look like, because those are fascinating tools for understanding network communications and protocols. This is not a good page to use. Let me use something else. Let's see if this will load up. There we go. Boom, the BBC. All this information. Look at all this networking stuff going on. Oh my, this is crazy or what? That's what happened to create this one web page. So there's the start, bbc.com. I mentioned some verbs, right? I said get and put. Look at this, get. So I executed an HTTP command, the verb get, to get the page pointed to by this URL, to which it will give me its default page. I'm talking to the server, right? And it gave me a 200 code back, which is the OK code, saying that the command completed properly. It told me the address and the port that I'm communicating with. So the first part there, up until the colon, is the IP address for the BBC server I'm talking to. And port 443, that is the TLS port. So all the data is encrypted. Now, the reason that I can see the data in the browser, because by the time it's in my browser, it's been decrypted. So here's the actual like request headers. Look at this. There's the site, the get, the scheme, what type of data I can accept back, cookies, which have all kinds of information basically about yourself, right? Your computer. What I'm using, Microsoft Edge, the operating system I'm on, all this extra information is sent to the computer, the server that I'm talking to. So it's all this kind of information that is used to profile computer users on the network, analyze, hey, what's the most popular, web browser? Well, you can get a sample of headers, logs, from web servers and just take a look, right? And you can see which browsers are the most popular, which operating systems are the most prevalent and whatnot on the internet. Now, when the page comes back, there may be a bunch of other stuff. So here's some, it's telling me I need this JavaScript. Okay. And then I need a style sheet, to make it look good. And you could look at here's the response. This is the actual style sheet that came back, which determines what the BBC web page looks like. We can look at some of the JavaScript. This is obfuscated code, so you can still read it, but like these variables, they've stripped them down and made them real simple, just single characters, to minimize how much data is sent over the network. Makes it harder to read, obviously, because you don't know, well, what's S and A and R and all that, but that's how you speed it up. Here's an image. I should be gray placeholder. Yeah, that sounds about right. More. Here's another image, a WebP image. The images, right, that I'll load it in. You can see them right there on the website. More JavaScript code, more images. So a ton of stuff came along, and you may have noticed there's all these little windows up here at the top of the screen. Everything is timed, so you can see, okay, I sent a request, waiting for server response, content download. So the request went really fast, and you've already seen ping commands telling you, how fast your data is flying over the network. But then the server was slow responding relative to the request. You notice that 8.5 milliseconds, where my request only took 0.3 milliseconds. Then once it processed it, or it was processing, so when it says waiting for server response, that is the server getting the file, getting the thing that you've asked for. And then the content download phase began. So it's basically giving me the time the first byte arrives. Microsoft Ignite. Interesting. So by the time the first byte arrives, it starts a timer, and then when it's done, it stops the timer and gives me the duration. So the content download was also very fast, less than a millisecond. In the old days, you'd never have this much stuff for loading a single web page. A lot of this stuff is probably going to be like advertising information. So you're really talking to a lot of different servers, and you can, um, I mean, you can see that. You go back to the headers, and so I'm talking to an image server there, and then I don't know, match.prod.bidder.io. That sounds like matching product, but I don't know. I don't even know what that is. We could look it up. There's internet tools we could use to figure out, who is our computer talking to? You know, there's some other bizarre website. I mean, we're talking to tons of different websites just loading a single page. It's kind of crazy how complicated things have become. Um, Probably talking to 20 or 30 different websites in that one request. I'm not joking. But that's client server distributed computing. Because as client server grew, the whole notion of distributed computing emerged. What do I mean by that? Well, we don't just have one web server, one BBC server doing all this work. I just said there's at least like 20 different servers we're talking to. Some of them, all they're doing is sending pictures. So there'll be a server optimized for sending images, a static image server. The images are probably all loaded in memory on the computer because having them all in memory ahead of time is faster than loading them in from the hard drive every time somebody asks for that image, right? And then people realized, well, we can make it even faster than that. I don't want all the requests for the BBC going to England. I'm going to put BBC content all over the world in edge servers. So the pictures and the stories are probably loaded in an edge server somewhere close to me, right? Or close to you, wherever you are. So that traffic is, gets to you quicker. It's more responsive. That's a type of, geographic distribution. You're spreading out the load of the overall system through distributed computing. But these different types of computers, image servers, ad servers, there may be just specific servers that are just sending, I don't know, just sending the JavaScript code, depending on what's going on. All those things, they create a great big distributed system, but it means that one computer doesn't have to do all that work. And they don't just serve the BBC, for example. So the same ad server that this web page may call, like there's a Mixbook ad, okay? So somewhere in here, it got an ad with this, little Mixbook logos. There might be a way to search through this data. I can't remember. Yeah, I wonder if I can find it. Let's see. I mean, it might not be as simple as just typing Mixbook. Well, maybe it is as simple as typing Mixbook. What do we got here? Definitely found some stuff. Let's see. Partner domain. Yeah, there's all kinds of Mixbook stuff here. So these, other websites will also talk to, yeah, this is part of the Mixbook imagery right here. They will talk to the same server, ads.us.criteo.com. So the BBC talks to it, but Yahoo might talk to it, or Google, or whatever, right? Advertising's everywhere. So you have this distributed system, which is an evolution of client-server computing. So now my client is not just talking to one server, it's talking to multiple servers that all work together to build a giant computing system. All right, so we talked about the first messages, telnet, client-server computing, how it's evolved, bulletin boards built on telnet, then the internet, the World Wide Web specifically, and how it's built on HTTP. So your browser is the client, right? Browsers took a few years to get right. Websites, or that's where the servers are, right? This distributed computing notion. And they might not just be one company anymore, right? The advertising company and the image company and the news story, all these things. That's the distributed computing part of it. Yeah, web browsers took a few years to create. Took some really smart people reading the protocols that were written by Berners-Lee to figure out how to implement and write a graphical client-based application. And the first one, I guess, was Netscape Navigator. Netscape became a really big, valuable company quickly. And everybody used Netscape Navigator if you had internet access. And again, at this point, you're still on a modem, but now instead of connecting to just individual bulletin board systems, see, and every time you connected to one, that's all you could do. You couldn't connect to like two at a time. You got to connect to one. I think well, no, I'm not going to bother. There's another one that I can connect to right now that I was looking at earlier. It was showing just a different piece of software that somebody had written for connecting to modern day systems. But you don't need to go into that. Now, Netscape Navigator came along. People got ISPs, Internet Service Providers, and they would connect to them, and then they had networks that connected to the internet. That's where things started to get real interesting, because now we have all these autonomous systems connected together through routers and firewalls and network address translators and things to construct a distributed network to go along and support our client server distributed computing paradigm. I know it's getting it gets pretty wild quickly. So the backbone of the internet, the fundamental services, they're all out there in this distributed system. You've been using some of them. Whenever you type NS lookup, you're talking to a remote computer system. I don't know if you realize that. Why don't we do that? We'll see what an NS lookup looks like in Wireshark. So we're just going to do the same one we already did. Clear my filter. Oh, I think I can run it again. We'll just run it again. There. Okay. Now, can I find an NS lookup command? Ooh, this might be tricky. So I don't know what protocol it uses. I don't know if it's UDP. See, I'm seeing a lot of UDP data right now because I'm in a video call, right? And it's using UDP. Oh, I might be able to find it by port. Well, I'm not going to go down that path. I don't have enough time to show you that. But the point is, when I type in NSLOOKUP and I give it an IP address, where does it get that information from? It doesn't get it from my computer. Right? It has to go somewhere else. That somewhere else is my DNS server that I'm using, which is a computer on the internet. And it lets me look up information on, network names. So you type a name in your browser and it uses a DNS server to get the IP address. And that's how you then communicate and send data to and from, like you see in Wireshark, right, with sources and destination IP addresses. Now, other commands, networking commands, don't use a remote computer. Um, like netstat doesn't necessarily connect to it. It just reports on your connections that you have on your system, depending on how you run it. If you run the slow version of it, it actually does name resolution, so it is making networking calls out to a DNS server. But some of you, I believe, are running it with a -N. I believe -N was the right command, and it runs really quick because it just gives IP addresses and doesn't give um, the names. It doesn't do the lookups of all the names of the websites that you're currently in communication with. But you could see if it was running in slow mode, you would see a whole bunch of DNS traffic when you're using Wireshark. Okay, hey kitty, my cat's here to say hello. Now, you want to come up, Sancho? Oh, come on. Nope, it doesn't want to come up. All right. So networking commands often use the network ping, for example. It's clearly going to use the network. You can see that in Wireshark. Now, these distributed systems, the network, the ISPs, they let you connect. So you connect to the ISP, and then it was able to give you an IP address now. Now you have a public IP address. You're attached to the internet, and you're able to route traffic to other public IP addresses, go through their address translator, go through their firewall, get to their web server, and say, give me a web page. And that web page would come back to you. And that's the World Wide Web in a nutshell, how it would work, right? Then it's become more and more advanced. Here's the guy. More security built in between the clients and the servers, so encrypted communication protocols, right? Because people were able to sniff traffic, and if traffic was plain text like Telnet, you could just read whatever anybody was doing. And that was, that was no good. So where are we today? Gosh, SSH came along as a superior protocol for remote connectivity with computer systems. So Telnet was plain text. SSH is encrypted, uses digital certificates, the same type of encryption that we use to secure your communications to and from a website. SSH works the same way. It is a client server protocol, but all the data is encrypted. VPN, right? You have a VPN client and it connects to a VPN server. Another example of modern client server communication protocols. And I think what other common protocols are out there? Well, talking to the mail servers, they have their own protocols. But people don't really use don't use a separate mail client anymore. I think those have pretty much gone away, and everybody uses webmail, or they run their email through a web browser. But there was a Windows, for a long time you could have Outlook was the name of their mail client, and so it would talk one of the mail protocols like IMAP, POP, SMTP. IMAP's the modern one. SMTP was so old that you could use, you could do it over Telnet and execute email commands. People used to do things like that where they would spoof an email address and use Telnet to send email from a fake email address. But you could enter somebody's unprotected mail server over the internet and basically trick it into sending mail for you. So you could impersonate people that way. I think most people have probably closed down those mail servers to prevent that from happening now. But there may still be open servers out there somewhere that people are exploiting. The protocols that we're using right now, real-time streaming protocol, RTSP, that's the protocol that's in use right now as we are in this call. It is a UDP protocol, so you'll see tons of streaming traffic going by. I'll turn it on again in Wireshark. So there's the Wireshark window. We will activate. There it goes, all this UDP traffic. Everything there is the words and the video, my audio and video. And that's like, just about everything my computer is doing right now is that traffic. And we could look it up. All of this stuff, this is my computer right now. That is my, should be my IP address, right? Okay, well, yeah, that is my IPv4 address on my private network at home. And then I'm communicating to that server. And I think we'd find if I tried to identify that with a reverse lookup, that is that's an Amazon web address that GoToMeeting uses. They have a server, bunch of servers in the Elastic Compute Cloud. So my GoToMeeting client gets assigned a server to communicate with to run this meeting. And then when you connect to it, you have the ID of the meeting, or like a link to it. And you don't know the IP address, right? You just have this ID. So you go to some type of server that GoToMeeting runs, some, kind of like an entryway server, and it looks at your meeting ID and looks up what internal server is running that current session, that meeting, and gives you that IP address. So now your client then can just go straight to the server that's running the video meeting. So that's how that works roughly. There's going to be more to it than that, but that's the gist of it. All the data is encrypted, as I mentioned before. It's all UDP, but here's the data. You can't read anything. Can't read anything in there. Somewhere in here, it might say what type of encryption. Although it's most likely that happened at like the very beginning, the very beginning of the session. So you set up some initial communications and share some data back and forth to say, hey, I can use this encryption protocol. Okay, that one's good. We'll use that one, and then you use that same one for the whole session. I don't know how RTSP does that. I can tell you loosely how web browsers do it. They use something called cipher suites. They have cipher suite negotiation for setting up secure communications, because some systems might not all have the exact same encryption capabilities. So they would have, cipher suite, I'll just call them A, B, and C. And the server might have C and B, and your client might have A and B. And so you negotiate. You say, hey, I want to use cipher suite A. And the server says, I don't have A. You can't use A. Do you have B? And you go, oh, yeah, I got B. So boom, now you have done a handshake, exchanged the cipher suite protocol that you're going to use, and you can start sending encrypted traffic back and forth. Very loose, very rough explanation of how encryption negotiation works. There's a little more to it, but that's the general idea. Let's see, what else? What else? What else in client server computing? Now we have the cloud. So all the servers in the cloud we don't really talk to them any differently than how we talk to anything else over the internet, except that the infrastructure itself is different because the cloud infrastructure supports lots of different people using it for running their businesses. So there's a lot of different tools and features, services, security features, things like that built into the cloud that we didn't used to have when you're just running a website. Certainly not if you're just running it from your basement, but like if you did web hosting, 30 years ago, which I was doing, then you had a company that you would hire, and they would give you, uh, either a whole server or just part of a server, and maybe they're running some virtualization software on it. They might be running more than one web server on it. You could have more than one network interface card in the server so that you could have multiple IP addresses, and then each server within each web server within the physical server would use one of those network interface cards to handle traffic. Now it's done a little differently. Basically, everything's going to be cloud-based. A little different, but a lot of the principles are the same. Um, each of the key difference with the cloud and why it's different than just any old data center is 20 years ago, you ran your own data center if you had a big business. And most of the computers in that data center were not being used all the time. Your utilization was 15%. So you're taking up space, you're making heat, you're wasting electricity. Not good things, right? So the virtual software companies came along and said, hey, we're going to make your stuff more efficient. So VMware came along. Now, there's probably some others before them, but we'll just use them. And they said, hey, you know what? We're going to let your server run, 5 different operating systems instead of one. And now it's going to be able to act like 5 different servers. So you could have your own distributed system, right? That's kind of cool. Distributed system, all on one server. So now you can get rid of those other servers. So people did. You would get one server, load it up with tons of memory and multiple cores, multiple CPUs, multi-core chips and stuff, hyper-threading and all that. So you could have a lot of logical threads and a lot of memory. Maybe multiple network cards, depending on what you're doing. And now that one server replaces 5 servers, for example, or 10. Much more efficient. And then Amazon was like, oh, that's kind of cool. How about we create, cloud computing? And we're going to put up banks and banks of servers and set them all up with virtual machines in them and hook them up to storage and networking and all kinds of extra monitoring tools and sophistication and security and network security, physical security, all the services you need. You can remotely connect to them. So you use SSH to connect into your Amazon cloud instance, deploy code, and run your systems. And cloud computing, as the next major shift takes over. So client server, then distributed computing, now cloud computing as another extension of that same fundamental model. It's a type of distributed computing. Now we have all kinds of new clients and servers, all that AI stuff, right? So we have AI computers and servers out there. We've got quantum computers that you can communicate with now and send jobs to uh, through Microsoft Azure, right? It has quantum computers that you can rent. They can't do much, but you can play around with them. You can do it for free. I did it one class and showed, how you could do it. Anyway, that is my talk on distributed computing, client server computing, how it's all shaped up over the last 50 years or so. All right. Hope you enjoy this. Bye bye.